This is Euclid Book 6, Proposition number 20, Part 1. Oh, this is going to be in multiple parts. Just guarantee that right now. And I guarantee you that Booba1067 is going to comment on this. I hope she does. I would be thrilled if she did. Okay? Now, here's the situation. Look at this polygon. This is what they call a polygon. And I'm not talking about this that you'd say, well, there's a square there. Well, actually, that's not really so much of a square. If you really looked at the dimensions of this thing, it really is not a perfect square. Okay? But that's not the polygon. The polygon starts from here, up to here, down to here, down to here, down to here. Almost like a pentagon. Okay, this would be kind of like a pentagon, but it's funkier shaped even than that. So this is one of those really funky polygons. Okay, so you say, well, a pentagon is a polygon. That's true, but this is even weirder than an ordinary pentagon. So this is really a funky polygon. Okay, so you take a look at this thing, and you're like, holy cow, now how am I supposed to say that this thing is, say, like twice as large as this thing? See, this drawing here is shape-wise identical to this drawing up here, but as you can plainly see, this one here is much bigger than this one. And in this particular case, this is at a 2:5 ratio. Okay, now we've been talking about ratios for a long time now. If you don't know what ratios are, you need to go back to the beginning of book 6 and start again. Okay, so we are saying that this is a 2:5 ratio, 2 parts to 5 parts, and this becomes very important if you're doing chemistry, if you're doing physics. You're going to have to know ratios. Okay, they may ask you to make a model car and then make the full-size version from the model car. Now ratios and proportions become important. Okay? The first thing I'm going to tell you is that these are not perfect. Okay? I have spent days trying to draw this thing and this thing, and I can tell you right now that they are not exactly, my drawings are not exactly in a 2:5 ratio. I tried hard, but actually a couple of these lines are a 1/4 of an inch longer than what they're supposed to be, and I'm not really sure where I went wrong. I don't know what the mistake was, but I ended up with 2 of these lines being a 1/4 of an inch longer than what they were supposed to be to make this a 2:5 ratio. Okay, but forget all that. Alright, now if Booba1067 wants to draw this a little more accurately, she is welcome to, and she is welcome to tell us exactly how long each one of these lines has to be to make this exactly a 2:5 ratio. That would be wonderful. I hope she does. But what she wanted me to do is try to explain this to you people in the simplest terms possible, because like I said, some of my audience here, they're still not quite out of arithmetic, so now we're having to explain this in a little simpler manner. Now, let's say you've got a softball and a tennis ball, and we established that the softball for some reason ended up being twice as large as the tennis ball. And you say, well, how are you going to prove that? Well, what we would do in that case is we chop the softball and the tennis ball in half, and we'd say, well, if the left half of the tennis ball, if the left half of the softball is twice as large as the left half of the tennis ball, and the right half of the softball is twice as large as the right half of the tennis ball, then therefore the softball is twice as large as the tennis ball. Of course, you would never be able to use them again unless you stitched them up, but there you go. And that's what we're going to prove here. And I'm going to go ahead and stop this video right here because we have actually explained what we're going to try to prove, and then I will actually physically take you through the whole proof, and hopefully you'll see what you need to see, even though the drawings are not 100% accurate. I know you probably can't tell that from the video, but they are not 100% accurate. I did my very best to make them 100% accurate, and they just didn't come out quite. This line right here ended up being a 1/4 of an inch longer than it should have been, and this line right here also ended up being a 1/4 of an inch larger than it should have been. But aside from that, these drawings are as close as I could possibly get to making these drawings the way they should have been. And hopefully you will see, as we do the proof, that we have a 2:5 ratio between these two polygons. And what we've done is we have actually divided these polygons into one, well here, I'll go with the bigger one here, into 1, 2, 3, 4, 5, 6, we divided it into several triangles. We took the big polygon, divided it into several triangles, and said because the triangles are in a 2:5 proportion, therefore the whole polygon here is in a 2:5 ratio with this one. So 2:5 ratio between the two polygons. And we established this by dividing this polygon and this polygon into a series of triangles and said these triangles and these triangles are in a 2:5 ratio, therefore so on and so forth. But like I said, I'm going to take this through real slowly with you guys. I know the drawings are not 100% accurate. If Booball 1067 comes up with better calculations, I welcome it 100%. I did my best, people. I really did. So anyway, this is kind of the beauty of mathematics, and I will continue this proof, so stay tuned.